Okay, so we have already started this chapter, but I'm going to try to weave in some review as we go along here. So we're talking acids and bases. We are going to talk primarily about acids today, and we're going to start off with some vocabulary. Okay? First things first, polyprotic. What does the prefix poly mean? Many, more than one, multiple. Polyprotic. Protic means protons. If you would please go back and look at the introductory notes. What is our definition, guys, of an acid? Not from Chem 1, but now. What do acids do? They donate protons, or another way to say that is they donate hydrogen ions, because remember, a hydrogen ion is really nothing more than a proton. Polyprotic acid thus means an acid that has more than one hydrogen to give away. And we can even be more specific. Diprotic, an acid that has 2 hydrogens to give. Triprotic has 3. There's no such thing as a tetraprotic acid. What would you call an acid that has only 1 hydrogen to donate? Monoprotic. And most of the acids we will be dealing with will be monoprotic. Okay? Here's another one. We've seen this word before, oxyacid, and it means exactly what it sounds like. An acid that has oxygen in it. Now, for the most part, that's going to mean an acid that has hydrogen joined to one of our polyatomics. Okay, that's where we're going to see that the most often. And then there's another type of acid, organic acids. We're not going to talk about these very much in these next 2 chapters. We will see these more when we get to organic. Okay? It just means an acid that has a carbon chain backbone to it. Still has a hydrogen to give away. Okay? Very weak acids, but we're not going to get into this much at all. Okay, until the end of the year. Here's another vocabulary word you need to know. Amphoteric. Amphoteric means has the capability to behave as an acid, but can also behave as a base. Now, let's review that. Okay, we said acids are things that donate hydrogen ions. So what's a base? What do bases do? They accept hydrogen ions. They accept a proton. And water is an example of something that is amphoteric. It's not the only example. Okay, but if you look at this reaction here, this is showing you what happens to water if it behaves as an acid or if it behaves as a base. If H2O gives away a hydrogen, that would be acting as an acid. What is left of it? Just OH minus. When H2O acts as a base, accepts a hydrogen, it becomes this ion. Do you remember the name of this guy? Hydronium. Very good. Okay. Some terms we learned at the beginning of this chapter: conjugate acid, conjugate base. These are terms that are primarily going to come up in multiple choice. You know, here's a reaction. Which of the following species is the conjugate base? A, B, C, D. Okay. Remember, conjugate base just means whatever your acid becomes after it donates that hydrogen away. Your conjugate acid is whatever your base becomes after it accepts that hydrogen ion. Okay, so just review that vocabulary a little bit. Okay, but water's not the only thing that could be amphoteric. For example, this ion, this is one of our polyatomics. This is another example of something that is amphoteric. If this ion, ladies and gentlemen, behaves as an acid, what would it become? What would this guy's conjugate base be? SO4 with a, what kind of charge? -2. Okay, that's sulfate. SO4 with a -2 charge. So if this gives away a hydrogen, it becomes sulfate. What if this acts as a base and accepts a hydrogen? What would it become? H2SO4. That's sulfuric acid. Okay, so water's not the only thing, but it's a good example. Here would be another one. Okay. All right. Guys, what does a capital K as a variable, not a unit, I don't mean Kelvin, what does this represent in chemistry? An equilibrium constant. Okay. And we've seen a few of these now. We've had Kc, Kp. When we started this chapter, we saw some Ka values. Here's another one. If you are concerned about keeping all of these straight, please don't be. On the front side of your equation sheet, guys, on the right-hand side, these different K values are listed for you. And in parentheses, it gives you sort of the circumstance under which you would use them. Okay? But does the little letter really matter? Yes and no. But the point is, equilibrium constants, no matter what that little subscript is, products over reactants. All right, well, this KW, anybody want to guess what W stands for? Water, is very specific for this particular reaction. Products over reactants. Now, how come the reactants are just sort of not there? Yeah, liquids. Liquids get excluded. Now, let's also talk about why does this say H plus instead of H3O plus? Well, this is sort of the longhand way to write this reaction. Sometimes you'll see it written a little bit more simply, like this. Like that. And if you look at the reaction written a little bit in a simpler way, think of it as like a shorthand way, then that's where this is coming from. But guys, the important thing is here, H plus and H3O plus, they're representing the same thing. Please don't get hung up on, well, is it H plus, is it H3O plus? You can think of those as basically the same thing. Right? KW is kind of special because not only is it for a specific reaction, it has a specific value. Please don't memorize it. It's right here. It is given to you. Okay? We are going to be living in this little area of your equation sheet a lot today. Okay? There's very little memorization. All of the equations we're going to use today are all given to you. And this is one of them. So you don't need to memorize this number. Okay? It's the equilibrium constant for water. And let's just make sure that you understand when we use terms like neutral, acidic, basic, I want to make sure that you know what you're really talking about. Okay? If I say that a solution is neutral. What kind of a pH does it have? 7. Well, that's great. I'm glad that you know that. But I also want you to know a little bit more. What neutral really means is that these two molarities are equal to one another. And to be more specific, knowing this equation, this relationship right here, if these two things are equal, then we're talking about a molarity of equal to this number. Shame on me for not putting units. That should have units of molarity right there. -1 for Miss G. Shame on me. Okay, if we say something is acidic, what kind of a pH are we talking about? Somewhere below 7. Okay, well, what that really means, to have a pH below 7 means whatever my molarity of hydrogen is, the ion there, is greater than hydroxide. And vice versa if something is basic. This would be a pH greater than 7. Okay. So when we use these terms, I just want to make sure that you actually understand what you're really saying there. Okay. Now, this equation, you are going to use 1,000 times over in the next month. This is the way to find pH. Okay, the most common way that we're going to use, it is on your equation sheet. It's there, but it really doesn't need to be there because honestly, guys, you're going to use this so much, you will have it memorized by the end of the week, if not sooner, because you're going to use it so much. Just make a note, make sure you recognize this is log base 10, not natural log, like we were using in the kinetics chapter. Different button on the calculator. Okay. We know there's a pH scale. Hopefully you know that there is a pOH scale as well. Okay. Very similar equation, just hydroxide instead of hydrogen. Okay. I'm sure you all know the pH scale is from 0 to 14. However, there is such a thing as a negative pH. There is such a thing as a pH greater than 14. That does exist. It's just that most of our pHs are going to fall in that range. Okay. I want you all to understand, those of you that are mathematically inclined already know this, but that logarithms are an exponential relationship. Okay. For example, if I say that the pH is decreasing, is this solution becoming more acidic or more basic? Which one? More acidic. Well, if something's becoming more acidic, then my hydrogen ion molarity must be increasing, and that is happening. I just want to make sure that you understand that as pH decreases, this molarity is increasing, not linearly, but exponentially, because that's how logarithms work. Okay? Now, please don't shoot the messenger. pH has its own rules for sig figs. Sorry. It's not difficult, though. Okay? Let me give you an example. Let's say I give you a very, very easy, simple calculation, okay? I give you the molarity of hydrogen ion, right here. Again, shame on me for not putting units, bad, okay? Here's my molarity, and I say to you, calculate the pH. Well, this one's really easy. Hopefully you wouldn't even need a calculator, but if you did, you took this number, negative log, this number, the number 8 is going to come up in your calculator as the answer. But you are not going to report pH equals 8. No, because you know better. Do you all agree that this number, the given information, which is always where you look to decide sig figs, do you all agree that this number has two significant figures. Do you agree? Okay. When you report a pH, the only numbers in a pH that are significant are ones that fall after the decimal place. 2 sig figs translates into 2 decimal places. Okay? And we could go the other way as well. Like, let's say, let me give you an example. Let's say I give you a pH of 2.613. And I say to you, please calculate for me the hydrogen ion molarity, the hydrogen ion concentration. First of all, let's make sure that we are comfortable doing that in your calculators, because this was a skill required on our last test, and many people did not know how to do it. If this number is here, and I'm probably using the wrong math term, so don't tell your math teachers, how do you invert a log? Like, that's probably the wrong word, but what do? Not e to the power of, because this is log base 10, 10 to the power of. If we want to go even simpler, in your calculator, all you do is second log base 10. And what should come up in your calculator is 10 to the power of blank, 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 blank. And it's waiting for you to put something in there. Be careful. What are you going to put in there? Thank you. Not 2.613, but I'm going to bring the negative over. Negative 2.613. Okay, so this is what comes up in my calculator. 0, 0, 2, 4, 3, 7, 8, dot, 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 and so on and so on. Where should I round that off? Which numbers are significant in a pH? Just after, so 1, 2, 3. So how should I round my answer here? 0, 0, 2, 4, 4. Yeah. Okay. And that's a concentration, so molarity. Right? So I just wanted you to be aware of this. Okay? And I'm sorry that we have this new set of rules. It's kind of annoying. But it is what it is. Okay? So, as we said, our pH scale goes from 0 to 14. In case you didn't learn this in Chem 1, your pOH scale, guys, is a mirror image, sort of. So, like, a solution that has a pH of 1 has a pOH of 13. Something that has a pH of 9 has a pOH of 5. What is pH plus pOH always equal? 14. Okay? All right, this is just showing you the relationships between the concentrations of the ions. All right, but here's the thing, guys. We have these 4 relationships. Don't memorize them. They are all on your equation sheet. They are all there. You can do a lot of things knowing these relationships. Specifically, I can give you one of these pieces of information. Maybe I just give you the pH. Or maybe I only give you the hydroxide concentration. I can give you any one of those pieces, and you can use these equations or combinations to solve for the other 3 pieces. And that's exactly what I'm going to ask you to do right this minute. So I'll get to this estimating in just a second. But the point is, For example, in number 1, I have given you the hydroxide ion concentration. So you have this. You can use these equations to solve for these other pieces. And guys, you and the person next to you might go in a different order. For you, maybe it makes more sense to use this and go right to a POH. Maybe that's what you choose to do first. Whereas maybe the person next to you uses a different equation and chooses to start here and solve for the hydrogen ion concentration first. That's fine. There's multiple ways to go. As long as we end up with the same answers, I'm happy. Try this, please. Okay, check them. Yeah, guys, there's multiple ways to do this. You may have solved for the POH first. Okay? There's different ways to go. As long as we get the same answers, we're in good shape. Okay, here are the answers for numbers 2 and 3. Please check them. I tried to put boxes around it so you could see it clearly. And yes, there is such a thing as a negative pH.
Yes.
You should interpret negative pH to mean like crazy acidic, like eat your face off acidic. Okay, now, guys, all you are doing here is taking numbers and plugging them into equations. Okay, this should not be difficult. This is just plugging numbers into an equation. And if it is difficult, then you need to come and see me because we need to work through it, because it's really not. Okay? Now, could you have questions like this on multiple choice where you don't have a calculator? Yes, you could. Now, do I expect you to be able to do logarithms in your head to the exact decimal? No. But I'm going to show you how you can very skillfully make some estimates. Okay? For example, you're in multiple choice, you don't have a calculator. You, let's say, are given this information right here in this red box. You are given an H plus molarity. And the question says, what is the pH? Okay, for those of you that are mathematically inclined, you may already know this. If I take the negative log of this number, which is exactly what you would do to find the pH, your answer will be very close to that exponent. Okay? Let me say that again. If you take the negative log of this number, your answer will be close to the number 11. So just knowing that in multiple choice would allow you to eliminate some choices. Like, there is no way that this is going to have a pH of 2 or 3 or 4 or 5. Okay? So here's the thing, right? Let me show you. If you had a number like 1.0 times 10 to the negative 11th, and you took the negative log of this number, you would get a pH of exactly 11. This is a number greater than 1.0, which in logarithms is going to translate to my answer is going to be slightly below the number 11. Okay? Now, how far below? Well, that's kind of where you're estimating a bit, but let me show you something. And if somebody would type this in, that would be great. Somebody take the negative log of 1.1 times 10 to the negative 11th. Tell me what you get. No, wrong. Try again.
I missed it.
10.95.
10.95? 9.6, okay. So this number is greater, but it's just a little bit greater. So this number is below 11, but just a little bit. This number is quite a bit greater than 1.0. So let's go extreme. What if I had like 9.9 times 10 to the negative 11th? Put that in your calculator, what comes out? 10.0 something? 4. Okay, so it's below 11 and it's like way below 11, but not quite to 10 yet, but getting close. So you should be able to make an estimate. So given this number, it's definitely going to be below 11, and it's going to be a pretty good ways below 11. Not quite to 10, but close. All right, so let's go the other way. What if, let me erase all of this. What if I gave you a pH of 2.98? Okay, let's go backwards. This would be something times 10 to the negative what? Third, okay. Now, whatever this number is, it's going to cause it to be a little bit less than 3, and this is just barely less than 3. What kind of a number would I expect here? Like 1.1? Yeah. Okay. So that is a good estimating technique right there. And let's say you're given something like this. 0.46. Okay, let's say it's on multiple choice. You're given this and you're supposed to estimate a pH. My suggestion, if it's not in scientific notation, put it in scientific notation. Tell me what this would be. 4.6 times 10 to the what? Negative 1. Okay. So this is going to be a pH of, can you give me like an estimate? Is it going to be above 1 or below 1? Below 1. And that's like almost to 5. So maybe 0.6. Maybe, well, let's see. Yeah. That's probably a pretty good estimate. Sorry, you can't see that. Like 0.60. Okay. Yeah.
Can you give an example of how
It can't. If this number is any number greater than 1.0, it will be below the exponent. That's always how that works. It'll be a number below your exponent. All right. So we're going to move up just a little bit more in difficulty, guys, and we're going to start to be given some acids, different kinds of acids, and we're going to calculate a pH. On this slide and the next one, I have a set of steps which I'm going to skip over for the moment. I will come back to them. Please don't try to write all of that down. What I do want you to focus on, or just listen, you don't have to write this down, is this right here. Okay? In this chapter and the next, it is absolutely imperative that you understand the chemistry. If you try to memorize, oh, this is this type of problem, this is this type, this is this type, it's not going to work because every question is different. Please don't memorize, understand it. That's why we're moving so slowly. That's why we're just going to creep up in difficulty. we are going to start with the simplest type of pH calculations, and that is strong acids. Can you refresh my memory, please? What does it mean for an acid to be strong? Complete dissociation, complete ionization, completely dissolves, however you want to say it. Strong acid calculations, guys, are quick and easy. You will love them because they're so quick. And here's why they are so quick. It's because of this relationship right here. How many strong acids are there in that mnemonic device? There are 6 of them. Can somebody name one? Perchloric? Okay. I'll go with perchloric. That sounds good. I'll use that as an example. Let's say that I have a sample of perchloric acid and it's a 5 molar solution. Okay. Well, guys, think back. What is the one piece of information that you need to calculate a pH?
The molarity of the hydrogen.
Okay. Yeah, the molarity of H+. That's what we really need. Okay? Here's the beautiful thing about strong acids. If you know the molarity of the entire acid, that is also the molarity of just H+. Which means you can take this number and plug it right into that negative log equation. And done. You're done. You found the pH. Now let's make sure you understand why this is true. Because of this. Complete dissociation. All of these HClO4s are going to split into H pluses and ClO4 minuses. However much acid I started with will all be converted into those ions. And that's all you have to do. It should make sense to you if we're dealing with a strong acid, which means a lot of hydrogen ion floating around, that there will be very, very little OH minus floating around. That should make sense to you. Because of that relationship. Now, there is something that comes up here, and it doesn't come up very often, but I wouldn't be doing my job if I didn't bring this up. And make a note, this applies to strong acids only. That's why it's on this slide. Okay. Somebody give me a different strong acid, not perchloric. Give me another one. Hydrochloric. Okay. Sounds good. Let's say we are dealing with hydrochloric acid and this beaker, this solution has this molarity. Okay. Would you say that's a big number, small number? Small number. Small molarity. What's the opposite of the word concentrated? A solution that's not concentrated is very dilute. This is an incredibly dilute solution right here. In fact, it is so dilute, its molarity is less than 10 to the negative 7th. It is so dilute. Here's what that means. This acid, even though it's strong, is so dilute, it is no longer the dominant acid in the beaker. Now, what's the definition of an acid again? What do acids do? They donate hydrogen ions. This is so dilute, water is in fact the dominant acid in my beaker. Water is giving away more hydrogens than this guy. And guess what? If water is your dominant acid, what do you think the pH is? 7. You got it. You don't have to do any calculations whatsoever. 2 sig figs, I would report this as pH equals 7.00. Now that is not going to come up very often. It only comes up if your molarity is less than 10 to the negative 7th, but it does happen on occasion. Okay, now let's practice our estimating. Let's say you did not remember this fact, and you said, okay, I've got to take the negative log of this number. What kind of a pH would this give you? Let's practice our estimating here. 8 point something. Okay. Well, 8 point something. How can an acid have a pH of 8 point something? That doesn't make sense. That's in the basic range. That's because you're not supposed to do that. Here is your answer. Okay. So, really quick, we'll do these together. This is so fast. Calculate the pH of. Skip over the number. This is the thought process I want you to go through. Focus on the compound. Is this one of our 6 strong acids? Yes or no?
Yes.
It is. Okay, now come back to the number. 0.20. Is that smaller than 10 to the minus 7th? No. So what are you going to do? What are you going to do with this number of 0.2? Negative log 0.2. Put it in your calculator. How many decimal places should my pH have? Okay, so round to 2. What do you get? You got it. Is that an acidic pH?
Yes.
You bet. And it should be. Okay? And that's it. Look at this one. Calculate the pH of. Skip over the number. Strong acid, yes or no? What acid is that? Nitric? Yes, one of our 6 strong. Okay, now come back to the number. Look at it.
7.
So our pH is going to be 7. And if you had to explain why water is your dominant acid, this molarity is so dilute that water is in fact the dominant acid. No calculation required. What's the opposite of strong, ladies and gentlemen? You got it. Weak acids? Not quite as simple. What does it mean to be a weak acid? Very good. They do not completely dissociate. We will have Ka values given to us. Did you notice on the previous slide we weren't given Kas, we don't need a Ka value. Strong acids, we don't deal with Kas. Weak acids, we will. Okay? When we start dealing with weak things, okay, we're going to start doing what's called writing out our major species. This is going to become really important next chapter. We're going to start at this chapter, but it's going to be critical in our next chapter. Okay? Weak acid problems are just like problems we have done before. We did this in first quarter. Do you remember? Oh yeah! Ice tables. Boy, do I hope that you like them, because guys, they are your life for the next month. Okay? If you did not care for them, I hope you can at least appreciate how they can keep your information organized. Okay? So, here we go. Guys, we are going to do this problem together, and I'm making some rules here. Okay? We're going to do number 1 together. And I'm going to pull up a blank screen in a second, and I'm going to do this problem. Here is the rule. I don't care what kind of hotshot AP Chem student you think you are. Whatever I write up here, you write. Because everything that I'm going to write on this screen, I will want to see in order to give you full credit on a test question like this. Okay? So here we go. If you need to stretch it out, stretch it out. Here we go. It says, calculate hydrogen ion molarity, hydroxide molarity, pH, POH. Stop right there. Do you guys realize, from a couple of slides back, if you have only one of these, you can find the other 3? You remember that? Okay, great. Find all of these things for a 2 molar acetic acid solution. Stop right there. Look at the acid. Strong or weak?
Weak.
Good. It's on a weak acid slide. It's probably weak. Okay. It is weak. Here's another clue that it's weak. We're given a Ka value. Strong acids don't have Ka values. Okay. So here we go. Whatever I write, you write. Let's list out these major species. Here's the first one that they tell us. It's that acid. Now, can somebody tell me, why do I write it like that instead of writing it like this? Don't write this down. Just watch and learn. Why didn't I write this particular acid split up? Because it's weak, which means it doesn't, what's the word? Dissociate. It doesn't, it barely dissociates. Now, if that were a strong acid, I would write them separated, but it's not. So we're not going to do that. Here's my other major species. You'll always have water. And guys, that's it. Those are my 2 major species. That's the only 2 players I have to deal with. So I'm going to add them together. Those are my reactants. Let's predict products. This was an acid, yes? What do acids do? They donate their hydrogen away. Well, if that happens, what's left of this guy? What polyatomic ion is that? Acetate. Okay. Where does that hydrogen go? It goes to the water. So what does water become? Oh, you guys are so smart. Yep, write it down, your 3 favorite letters. Suck it up, cupcakes. Okay, let's review. What does the word I stand for? I love chemistry. Yes, no. Initial. Initial what?
Initial concentration.
Molarity. Concentration. They gave it to us. Okay. Somebody tell me why I do this. It's a liquid. We don't care about liquids. They get excluded when we're talking about equilibrium. Okay, now my 2 products are aqueous in their state of matter, so I care about them. Let's see what you remember back from first quarter. These 2 players here are not mentioned in the problem at all. What does that mean if something is just not mentioned in a problem? How much of it do you have? 0. You have none. Now, believe it or not, guys, these ice table problems are actually easier than the ones you did in first quarter. Because first quarter, you had to figure out whether these things were shifting to the right or to the left. These are going to be shifting to the right always. You can tell that because it's 0, 0. What does C stand for?
Change.
Okay. Do you remember what we wrote here? Minus X. What about on the product side? Plus X. Here's something else that's going to make your life easier than in first quarter. These equations are always going to be 1 to 1 to 1 to 1. If you had coefficients like a 2 there, this would be minus 2x. You're not going to have to deal with that in these acid-base questions. What does E stand for?
Equilibrium.
You got it. Okay, I'm just going to bring everything down. E stands for equilibrium. Great. I'm going to write an equilibrium expression. What kind of K do you think this is going to be? Ka. Okay, this is an acid equation. And I'm just going to take these x expressions and I'm going to just plug them in. X times x, that's x squared. And we were given a value for Ka. I've got to solve for x. How am I going to do that? Isolate it. Okay, well, you could use algebra. That's going to involve the quadratic equation. Yeah, let's graph it. That's what we did first quarter. So let's review that, everybody. Let's remember what we did. Go to y equals. For y1, let's put the Ka value. All right, and let's be good science students. We're not going to type in 1.8 times 10 caret negative 5. No, you're better than that. You're going to put 1.8 e negative 5. You're going to put y2 as this whole expression. Remember, guys, it just makes your calculator happy if you put parentheses around your numerator and denominator. Just, it shouldn't be necessary, but just do it. You can hit graph if you want. I typically will go zoom standard, because that's just what I do. Now, this is review. You may or may not be able to see that intersection point. And guys, it's okay if you can't. It doesn't matter if you can't. We need to find the intersection point. Do you remember where to go to do that? Okay, second, calc, then intersect, and then what? Do you remember?
Enter.
Please don't move the cursor. Enter, enter, enter. If you did it right, this is what x should come up to be. Anybody else get that? But guys, let's focus on, let's try and find the pH. Tell me again, what's really the one piece of information you need to find a pH? Concentration of what? H+. Okay, great. Well, look up in our reaction. I don't see H+, but I see something that is essentially the same thing. H3O+. And what is its molarity? X. This is the molarity of H plus. Let's find a pH. Take the negative log of that number. Tell me what you get. 2.22. Okay. Now, I realize it said calculate a bunch of other stuff, but this is where I want to focus, is the pH. And guys, I'm going to ask you a question that you're going to get so sick of me asking you, because I'm going to ask it to you every single time we do a problem in here for the next month. Does this answer make sense? And I know what you're thinking. How do I know? We're just learning this. I don't know. It's an acid, right? Yes, nod your heads. Is this in the acidic range?
Yes.
Yes. Don't worry so much about where is it below 7. Is it below 7? Yes. Good to go. Think you can handle one on your own? I think you can. Do this one, please. All right. So, we okay? Ish?
Yes.
Okay. Now, I'm not quite finished, but let me show you something. Okay. What if? Look at this problem right here. I don't have just one acid. I have 2. And I know what you're thinking. Oh my God, does that mean 2 ice tables? No, it doesn't. Look at what my major species are. I have 1 acid. I have 2 acids. And I have water. Do you have to deal with both of these? No, you don't. You deal with whichever one is stronger. And how do you know that? Whichever one has the larger Ka. So which acid is that? Right. And guess what? That means you can completely ignore this other one. Okay, so let me make sure this is clear though. It's not that this acid doesn't exist, or it's not there, or it's not doing anything. This acid is contributing hydrogen ions, but it's contributing so few in comparison to this one that mathematically I can ignore it. So ignore it. This is all you have. How do you solve an HF and water problem? What do? You do an ice table. And guess what? Let me go back. In case you hadn't noticed, it's the same acid we were just working with. Okay, let me find it. There it is. All I want you to do, ladies and gentlemen, let's make this really quick. It's the same exact acid, which means it's going to have the same Ka value. What is the only number in this ice table that will be different? The initial molarity. And what is it? 1.2, I think? Let's make this really fast. Go in your calculators. All you have to do is change one number. Change this number to 1.2. Tell me what X comes out to be. Point what?
029.
Okay. So what's the new pH? 1.5.
1.5.
4?
Yes.
Okay. There you go. So guys, don't be scared by a mixture of acids. It just means you have to deal with the one that is dominant. What would you do if you had two acids? One is strong, one is weak. Do you have to deal with both of them? Which one would you deal with? And ignore the weak one. If you have two strong acids, now you do have to deal with both of them, but we'll get to that. Okay? So we'll stop here.